This is the third video in my series, as simple as 1, 2, 3. You surely remember that in this series I am talking about the apparently absurd result that's floating everywhere on the internet. The formula that the sum of all the natural numbers is minus 1 over 12. In the first lecture, we had seen that this series cannot have a sum according to the definition of the sum of an infinite series that is usually used. So, in order to make sense of our formula, we must look for an alternate definition. Before we do that, however, let me alert you about the nomenclature that we are following here. As you must realize, we will be discussing many series for which a finite sum does not exist in the conventional sense. We must try to make sense of their sum by going beyond the conventional definition. However, we will keep on calling a series divergent if it is a divergent series according to the conventional definition, irrespective of whether the series has a finite value or not, according to any alternate definition that we may find. As a result, we will be often talking about a finite value for a divergent series, which may appear to be oxymoronic at first glance. Our sum, 1 plus 2 plus 3 plus 4 all the way up to infinity, equals minus 1 by 12, is often attributed to the man who knew infinity, Srinivas Ramanujan himself. While Ramanujan's second letter to G.H. Hardy did mention this formula in passing, the formula itself dates back at least a couple of centuries. Ramanujan, with no formal mathematical training, had been unaware of the works of greats like Euler and Bernoulli, and he definitely rediscovered this result for himself. Now, as we all know, it was G.H. Hardy who introduced the world to the genius of Ramanujan. Once the latter joined him in England, the two had gone on to develop many wonderful results, including a large number of results on divergent series. Long before he'd met Ramanujan, however, Hardy was already the world's leading expert on divergent series. He was perhaps the first person to develop a mathematically rigorous theory of these entities. He was the first to lay down the formal structure of an alternative definition, which will allow us to talk about the sum of such series. Hardy gave all these alternate sums a name that he borrowed from a favorite fictional character of his. After the hero of Charles Dickens's first novel, The Pickwick Papers, he called such sums Pickwickian. Maybe it was the somewhat eccentric features of Samuel Pickwick's character that inspired this choice of name. Eccentric though these sums could be, they could not be completely arbitrary. They must conform to some basic expectations of what a sum should be. Indeed, it would have been great if it had been possible to maintain all the basic properties of our favorite sum of finite number of terms. But this is, of course, too much to ask for. We already know, for example, that rearrangement of the terms of a sum of a finite number of terms cannot change the sum, whereas this very simple property does not hold for even the conventional definition that we use for the sum of infinite series. It fails definitely for conditionally convergent series. So we have a decision to make. Which properties of a finite sum must be retained and which can be done away with? After a lot of thought, Hardy managed to reduce his list of properties desirable in a sum to 3. The first of these, the first Pickwickian property, is as follows. If the Pickwickian sum of a series A0 plus A1 plus A2 plus etc. is S, then for any finite real number k, the Pickwickian sum of ka0 plus ka1 plus ka2 etc. ad infinitum is k times S. This, of course, is the analog of the distributive law for finite sums, a property that we would want to continue for our so-called Pickwickian sums. The second Pickwickian property that Hardy wanted to impose on his sums is the following. If two series A0 plus A1 plus A2 etc. and B0 plus B1 plus B2 etc. sum up in the Pickwickian sense to S and T respectively, then the series that we obtain by adding the two series term by term, that is A0 plus B0 plus A1 plus B1 plus and so on, will sum in the Pickwickian sense again to S plus T. The third and final Pickwickian property is, if A0 plus A1 plus A2 all the way up to infinity add up to S in the Pickwickian sense, then the series A1 plus A2 etc. that we get by omitting the very first term of our series has a Pickwickian sum given by S minus A0. Here we have written this same property in a slightly different, although of course equivalent manner. I am sure that you will all agree that these properties are very reasonable ones to ask for. We may of course hope in addition that if the original series were convergent, that is convergent according to our conventional definition, then the series will also stay convergent in the Pickwickian sense. On top of this, it will be great if in such a case the Pickwickian sum were to match the conventional one. But this may sometimes be too much to ask. Alternate definitions of the sum that provided the same answer as the conventional sum if the latter exists are called regular. Sometimes in our attempts to sum up wilder and wilder series, we may have to give up on regularity. Let us now turn to the kind of series for which Pickwickian sums play a really important role: divergent series. Let me remind you once again that this name is given to all series which do not converge in the conventional sense. For a particular divergent series, it may be possible to find a definition of the sum that, along with satisfying the three Pickwickian properties, also manage to assign a finite value to this particular series. However, one should not really be taken by surprise if this finite value, the so-called Pickwickian sum of the series, ends up having a weird value. Let us now warm up to the final assault on 1 plus 2 plus 3 plus 4, etc. by trying our hand at finding out Pickwickian sums of some simpler divergent series to begin with. The first series that we will take a look at is not really very tedious. The series is 1 minus 1 plus 1 minus 1 plus 1, etc. up to infinity. Note that we are calling the value of this sum SP. The P suffix here is intended to help us remember that this is a Pickwickian sum, not a normal sum. The partial sums of this series form a sequence 1, 0, 1, 0, 1, 0 and so on. The sequence does not diverge to infinity, but it does diverge in the sense that it fails to converge to a definite limit. Thus, this series fails to be summable according to our conventional notion of a sum. It is a divergent series. Let us now see whether we can find a Pickwickian sum for this. Firstly, let us use the third Pickwickian property and separate out the first term from the series. Now we can make use of property number 1 to pull out a factor of minus 1 from the infinite series in the bracket. At this stage, what is left inside the bracket is identical to SP. Thus, the Pickwickian sum of our series obeys the equation SP equals 1 minus SP. This can be immediately solved to yield SP equals half. Thus, if the series 1 minus 1 plus 1 minus 1 plus etc. up to infinity has a finite sum according to some Pickwickian definition, then this sum must be 1/2. We need to stress this point once again. All the mathematical steps that we have carried out here will make sense only if a Pickwickian sum exists that will give this series a finite value. So while the steps carried out here obey the properties P1 through P3, and all these properties are obeyed by the conventional definition of the sum of an infinite series, we cannot use this argument that we have just given to claim that 1 minus 1 plus 1 minus 1 etc. has a sum of 1/2 in the conventional sense. That's simply because in the conventional sense, the sum simply does not exist. So once again, all that we can say at this stage is that if we find some protocol for determining sum that obeys the Pickwickian properties and it also yields a finite sum for this particular series, then that value must be 1/2. This definitely begs the question, does there at all exist a definition of the sum according to which this series can be summed up? We will come back to this point near the end of this lecture. For the time being, let us assume that for all the series that we are going to talk about here, we will be able to find Pickwickian protocols which obey the Pickwickian properties and which yield finite values for the particular sum concerned. It may be possible that one Pickwickian sum protocol can only sum up a particular series to a finite value and may fail to give a finite value for other series. All that we are assuming is that in the end, we will be able to find Pickwickian sums yielding finite values for each and every one of the divergent series that we will consider. Returning to our present series, 1 minus 1 plus 1 minus 1 etc., its value had been assigned to be 1/2 long before Hardy. As we have already seen, the partial sums of this series form the sequence 1, 0, 1, 0 and so on. From this, the famous mathematician Daniel Bernoulli had stated that the sum of the series must be midway between the two values 1 and 0 that the partial sums are swinging among. Indeed, almost half a century before this, one of the co-inventors of calculus, Gottfried Wilhelm Leibniz, had used a consequence of the binomial theorem 1 over 1 plus x equals 1 minus x plus x square minus x cube etc. to deal with this particular series. The expression we have on the right hand side is a special kind of series, a power series. The individual terms of this kind of series are not numbers, they are multiples of powers of a given variable x. So this is a kind of generalization of the notion of the polynomial, only there is no upper limit to how high the power of x can be. What Leibniz did next was to put in x equal to 1 into both sides of this equation, and from this he concluded that the infinite series 1 minus 1 plus 1 minus 1 etc. must add up to 1 over 2. Note, however, that the power series written here fails to converge unless the magnitude of x is less than 1. So what Leibniz really did was to take the limit as x approaches 1 from below. In advanced mathematics, there is a standard procedure by which we can extend the applicability of a power series even beyond the region where it converges. This is called analytic continuation. Indeed, we will see in a later lecture that analytic continuation will play a major role in summing up our target series 1 plus 2 plus 3 plus 4, etc. Now, although the formal theory of analytic continuation was developed a long time later, Leibniz could be given the credit of using it for the very first time in evaluating our series. There is, however, some scope of dispute about the precedence. Since Grandi, the priest who had first reported this result in 1703, and after whom this particular series is named might also have used similar reasoning. Be that as it may, for the time being, let us rejoin Leibniz. He did not stop at just evaluating the Grandi series. He had also used his newly discovered differential calculus to show that 1 over 1 plus x whole square is the negative of the derivative of 1 over 1 plus x. Substituting the latter with 1 minus x plus x square minus x cube, etc., and then differentiating this power series term by term gave him the formula 1 over 1 plus x whole square equals 1 minus 2x plus 3x square minus 4x cube plus 5x over 4, etc., etc. Here too, the power series on the right converges only when the magnitude of x is less than 1. But Leibniz was able to take the limit of x as it tends to 1 from below on both sides to sum up the divergent series 1 minus 2 plus 3 minus 4 plus 5 and so on up to infinity to 1 by 4. Of course, one may complain that this procedure of Leibniz is not mathematically rigorous. After all, not only does the series 1 minus 2x plus 3x square minus 4x cube plus 5x over 4, etc. fail to converge at x equal to 1, it is not even clear whether this term-by-term differentiation is legitimate when the original series of 1 by 1 plus x itself diverges at x equal to 1. Rather than try to provide a mathematically rigorous framework for Leibniz's calculations, let us see whether we can find a Pickwickian sum for this series 1 minus 2 plus 3 minus 4, etc. Once again, let me remind you that what we are really asking is, if there exists a framework obeying the Pickwickian rules that provide a finite sum for this series, then what should this sum be? Let us first denote our Pickwickian sum for this series by Sp prime. Let's now rewrite the terms in the following manner. We write the first term 1 as 1 plus 0, the second minus 2 as minus 1 minus 1, the third plus 3 as plus 1 plus 2, then minus 4 as minus 1 minus 3 and so on. Now we can use the second Pickwickian property to split this into two distinct series. The first one of these is our familiar Grandi series, which we have already denoted by Sp and evaluated to 1/2 in the Pickwickian sense. We now use a third property to split up the second series. Using the first Pickwickian property on the series in the brackets now shows that Sp prime equals half minus Sp prime. This immediately leads us back to Leibniz's result. So Sp prime does come out to be 1 over 4. This is not a coincidence. Leibniz's method does indeed satisfy the Pickwickian demands. So, 2 centuries before Hardy, Leibniz had really stumbled upon a proper Pickwickian sum. Now it's time to tackle our star series 1 plus 2 plus 3 plus 4 and so on. At this stage, it might be quite tempting to try to take another look at Leibniz's power series for 1 over 1 plus x whole square. Indeed, substituting x equal to minus 1 on the right hand side does change it to 1 plus 2 plus 3 plus 4 ad infinitum, exactly the series that we are now trying to sum. Unfortunately, the left hand side of this expression fails to give you any finite value when you put in x equal to minus 1, or a bit more precisely, take the limit as x goes to minus 1 from above. So, Leibniz's method, although it does work for the alternate sum of natural numbers, 1 minus 2 plus 3 minus 4, etc., it fails for the sum that we really want to do, 1 plus 2 plus 3 plus 4 ad infinitum. So at this stage, we will have to go back to the Pickwickian approach, hope that we will be able to find a summation protocol which will obey Pickwick's rules and be able to give a finite sum for our series. We will denote its Pickwickian sum by sp double prime, and then we will apply the Pickwickian properties carefully. As the first step, we split the terms as we did for sp prime. We write 1 as 1 plus 0, 2 as minus 2 plus 4, 3 as 3 plus 0, 4 as minus 4 plus 8, and so on. I am sure you can see the pattern here. The first term in each split has been chosen to be the terms that were there in our previous series, sp prime. The second Pickwickian property allows us to split this into two series as before. The first one, 1 minus 2 plus 3 minus 4 plus etc., is exactly the previous series, sp prime, whose Pickwickian sum is 1/4. A bit of thought will tell you that we can repeatedly use the property P3 to drop all the zeros from the second bracket. This will lead us to the series 4 plus 8 plus 12 plus and so on, which, according to the first of the Pickwickian properties, is 4 times sp double prime. So, our Pickwickian sum sp double prime obeys the equation sp double prime equals 1/4 plus 4 times sp double prime. This immediately leads us to the unbelievable but well-known result that sp double prime is minus 1 by 12. So, we have managed to derive Ramanujan's astounding formula. Or have we? Before we begin celebrating prematurely, let us ask ourselves, have we really managed to emulate Ramanujan and prove that 1 plus 2 plus 3 plus 4 ad infinitum is, at least in the sense of a Pickwickian sum, minus 1 by 12? I am sure that you will certainly realize by now that the calculation that we had carried out just now has a major flaw that needs to be rectified before we can claim to have proved this result. All that we have proven so far is that if there existed a protocol for summation that yielded a finite value for the series 1 plus 2 plus 3 plus 4 ad infinitum, and which at the same time obeyed the three Pickwickian demands, then the sum must turn out to be minus 1 by 12. What we have to do to make the proof really work is come up with a proper Pickwickian summation procedure that will provide a finite value to this sum. Indeed, since we have used the values of sp prime and sp as intermediate results in this calculation, our method must be able to yield finite values for all three of the divergent series that we have studied today. In our proof so far, we have just made use of the Pickwickian properties without showing that such a protocol really exists. To be honest, most of the so-called proofs of the Ramanujan result that you see floating around on the internet does argue along similar lines, maybe without even clarifying that the sum they are using is not the conventional one, but something which has to be defined afresh. Now this point needs to be noted with care. Even the conventional sum also obeys the three Pickwickian properties, but that definitely does not give us the right to claim that the conventional values of the three series sp, sp prime and sp double prime are 1/2, 1/4 and minus 1 by 12 respectively. The least that I can do before signing off today is to convince you that there does exist a simple Pickwickian summation procedure for at least the first of our divergent series, the one that we started working with today. The Grandi series, SP equals 1 minus 1 plus 1 minus 1, etc. up to infinity. This Pickwickian summation method actually dates back a long way. It is the invention of the Italian mathematician Ernesto Cesaro, series for which Cesaro's procedure happens to yield a finite value are called Cesaro summable. To find out the Cesaro sum, we first form the sequence of the partial sums S0, S1, S2, etc. as we do to find out the conventional sum. But then we form a new sequence by taking in order the first partial sum, then the average of the first two partial sums, then the average of the first three partial sums, and so on. If this sequence of averaged partial sums converge to a finite limit, then the series is Cesaro summable, and this limit is the Cesaro sum of that series. Now, the partial sum for the Grandi series are 1, 0, 1, 0, etc. The successive averages of the terms taken from this form the sequence 1, 1/2, 2/3, 2/4, and so on. It is easy to see that this sequence converges to 1/2, the Cesaro sum for the Grandi series. This, of course, matches the Pickwickian sum that we had already worked out, as it must. It is easy to check that the Cesaro summation procedure obeys the three Pickwickian properties. This actually guarantees that if the Grandi series is Cesaro summable, and we have just now seen that it is, then its sum must be 1/2. It is also easy to check that the Cesaro sum is regular. If we apply it to a convergent series, we will get the conventional sum back. The trouble for us is that it is too regular. For a series for which the conventional sum diverges to infinity, the Cesaro sum will also diverge to infinity. Thus, while the Grandi series can be handled by following Cesaro's procedure, this procedure will fail to work for both 1 minus 2 plus 3 minus 4, etc. and our star series 1 plus 2 plus 3 plus 4, etc. The power series method that Leibniz used works for both SP and SP prime, yielding finite sums for both. But it fails for our star series SP double prime. So our quest to prove that the sum of all the natural numbers is minus 1 by 12, at least in the Pickwickian sense, is not over yet. We will need to develop stronger Pickwickian sums that can handle these series and yield finite values for them. Only once we have such procedures under our belt can we convincingly say that at least in the Pickwickian sense, the apparently absurd formula 1 plus 2 plus 3 plus 4 plus up to infinity is minus 1 by 12 does really work out. In the next lecture, we are going to take forward our quest for stronger and stronger Pickwickian summation methods. Let's call it a day today.